Hi friends, I'm Professor Vayam Khan and this is the part 8 of unit number 2 block diagram and signal flow graph. From last few videos we are studying signal flow graph, and in today's video we are going to continue with signal flow graph. We are going to see some important terms which are involved in signal flow graph. And before proceeding to that, I'll request you to subscribe to my channel, like this video and share this video. Let us begin. So there are some important signal flow graph terms that you should know before solving the signal flow graph or before reducing the block diagrams or equations into signal flow graph. We have seen how to reduce the block diagram into a signal flow graph. We have seen how to convert an algebraic equation into a signal flow graph, but there are certain more things that are involved in this signal flow graph, and that these terms may appear or may come when you are solving some more numericals, okay, some more problems. So input or source node, all of you know what is source node or what is input node. A node with all outgoing arrows or all outgoing branches is called as source node. So here in this figure, x1 is your input node where all the arrows are going out. Similarly, its opposite is output or sink node. Okay, so in this output node, every branch is coming in. So this node has only incoming branches. So this x2 here is having all the branches coming in. Such a kind of node is called as output node, where all the branches, all the arrows are coming in, okay, inside. And this node is called as input node when all the branches or arrows are going outward, okay, out of the node. Then there is chain node, or also known as mixed node, where some of the arrows are coming in and some of the arrows are going out. It is a common type of node in which the arrows are coming in as well as arrows or branches are going out. So this node is called as chain node, or also known as mixed node, because it has incoming as well as outgoing branches. Then this is your forward path. Whenever we start from x1 to x4, or say start from input node to output node, the path traced during this input to output travel is called as your forward path. In only forward direction we are considering this, okay, no feedback, no reverse direction we are considering. We are considering only from input to output. In whichever way means there is possibility of going from x1 to x4 from a single path, okay, or you can say like reaching your destination from one road, and you can also reach that destination by another road, okay. There is another parallel road present for it, okay. So x for reaching x4 from x1, you can use this path, straight forward path, that is A, B, C, or I'll call it x1, x2, x3, x4, or you can also use x1, x2, this D side directly to x4. So these two paths are forward path in this signal flow graph. There is possibility of having multiple forward path in the signal flow graph, but forward path is always going from input to output. Remember that, okay, start to end, input to output node, okay. Any path from input node to output node is a forward path. Here we have only two. There is possibility of having 3, 4, 5 forward paths in a single signal flow graph, okay. So these are the four terms. Now let us go ahead and see some more terms. There is feedback path or feedback loops, okay. There are two different types here, feedback path and feedback loops. The function is same, but the name is a little bit different. Now this x1, x2, x3, x4, okay. Now if I come from x1 to x4 via x1, x2, x3, x4, this path. If I come to x4 by this path, this will be your forward path. Now I see here that there are some reverse arrows present here, like x3 is connected to x2. That means there is a feedback path present here. So this is a feedback path, or also known as feedback loop. Okay, so this is your feedback loop because it looks like a loop, because if you start from here, then you come to x3, then again you come to x2. So you come to the point where you have started. So therefore it is called as feedback loop. Okay, it is a path which originates and terminates on the same node. So for this specific portion, the originating point is x2, then you are coming to x3, then from x3 you are coming back to x2. So this is a feedback loop. Okay, this is a feedback loop. I'm again saying feedback loop. There is possibility that the originating and terminating path can be a single node. Okay, and you are not going to any other node before coming or before finishing the loop, like this. Okay, so you are starting from x3 and you are again coming back to x3 without going to any other node. Okay, so therefore this kind of node, or sorry, this kind of path or this kind of loop is called as self loop. Now this self loop can be in forward direction also, and it can be also in reverse direction. Self loop is a loop which starts and ends on the same node without connecting to another node. A special name for feedback path loop that consists of only one node is a self node. Okay, this is a self loop. Self loop. Okay, then there is your path, or you can say uh, uh, path is, it is a traversal of connected branches in the direction of branch arrows such that no node is traversed more than once. A path is simply the branch or the direction that is connected between two nodes. Say this x1 and x2 is connected by this branch, and it is showing direction in forward way. So this is a path. Again, this x2 x3, it is again connected with a branch which is having forward arrow. So this is also a path. Again, this one is also a path. This one is also a path. So path is a traversal of connected branches. Path is a traversal, means it is a group of connected branches in the direction of branch arrows. Okay. Now next one is path gain. So if there is path, that means if there is group of arrows connected with path, remember that it says when the branches are connected with each other in a specific way, then this path is also have a gain. The product of all branch gains while going through a forward path is called as path gain. जब भी आप फॉरवर्ड पाथ देखते हैं किसी सिग्नल फ्लो ग्राफ में, तो इसके जो ब्रांचेस का गेन है it gets multiplied, and that multiplied gain is nothing but the gain of that path. For example, if I consider path x1 to x2 to x3 to x4, this path x1 x2 x3 x4, this path, forward path, the straight forward path, this has branch, this one and this one, and they have gains a, b and c. So their gains will get multiplied. So a will get multiplied by b multiplied by c, and that will be the gain of this forward path x1 x2 x3 x4. Similarly, for path x1 x2 and directly x4, the gain will be a multiplied by d, simply d. Okay, so this is your path gain. Now then there is touching path. Touching path or touching loop is a loop, and when a loop and path are touching when they have a common node. Okay, now pay attention to these three loops. These are three uh, feedback loops. X5 is connected to X4, X4 is connected to X3, X3 is connected to X2. Now these three loops or these two loops have a common node. Whenever the paths or loops are having common node, then these kind of paths or loops are called as touching path. Now this first loop and this first loop and this second loop is having x3 a common node here, so they are touching to each other. Again, this second node and this second loop and third loop are having common node x4, therefore they are touching loop. Okay, while loops with one or more nodes in common are called as touching loops. They touch each other. Then there is non-touching loop. Okay, then there is non-touching loop in which there is no common node between them. So this x1 is connected with x4, x2 is connected with x3, x3 is connected to x2, x4 connected to x1, but there is no common node in between them. Okay, so therefore these kind of loops are called as non-touching loops. Okay, then there is loop gain. The product of the branch gains forming a loop is called as loop gain. The product of branch gains forming a loop is called as loop gain. Here the loop is, remember that whenever I'm saying loop, it means it is a, yes, it is a feedback path. It is a feedback path. Whenever I'm saying loop is, means that it is a your feedback path. Okay, loop looks like this. Okay, like this curvature. So the product of the branch gains forming a loop is called as loop gain. Here we have a loop x2, x3, x5, again x2. So we have this loop like this. So the gain will be L1 L2 multiplied by 1. So L1 L2 1 will be the loop gain for this loop. So you just need to multiply the gains of the branches present in the loop. जो भी branches loop के अंदर present रहेंगे, उन branches के gains को क्या करना है, multiply करना है, and you will get the loop gain. Okay. Okay, then there is your dummy nodes. A branch having gain 1 can be added at input as well as at output. Remember that when we are having signal RS and signal YS or CS, that is your input signal and output signal. So we need to add one node for them each. Okay, so we add one node for RS, we add one node for CS. So these kind of nodes are called as dummy nodes. Most of the time these dummy nodes, when connected with another node, they have a gain of 1. A branch having gain 1 can be added at the input as well as output node. It will not affect the transfer function because it is having gain equal to unity. So we have a gain equal to unity, therefore unity means 1, so it will not affect the transfer function of the system. Remember that the dummy nodes are added only at input and output nodes. Okay, so here at input node we add a dummy, at output we add another dummy. So these two nodes are dummy nodes. They cannot be added in between the chain. Remember that thing also. So this is your dummy nodes. There are some properties of signal flow graph. So we'll go through them quickly. It applies only to time invariant linear systems which are time invariant. Okay, so such a kind of systems we can use signal flow graph. So signal flow is only along the direction of arrows. Remember that signal flow means in which direction signal is flowing, like this x2 to x3. So in this direction the signal will be flowing. So arrow means that signal is flowing from this direction to this direction, or this point to this point. The value of variable at each node is equal to the algebraic sum of all the signals entering at that node. So that is your addition rule. Since the system equations of a system can be written differently, the signal flow graph is not unique. Okay, so if you have equation written, system equation written in a specific form, so it does not mean that signal flow graph is always unique. There is possibility of signal flow graph having signal flow graph in a different way. In different way means, like if you connect these x2 x4 like this, so it is possibility of connecting this x2 x4 in different way also, depending on the your system equations. So there is possibility of having multiple signal flow graph for same system equations. Okay, the gain of signal flow graph is given by Mason's equations. So we will study this Mason's gain formula in next video. This will give us the transfer function, or the value of the gain, total gain of your system, the whole system. In block diagram, what we do, we reduce the blocks uh, by different rules. For what? For getting the total transfer function of the system in a single diagram, or in a single block, so that we can solve it with the values of input and the transfer functions. Similarly, in this signal flow graph, we do not reduce them. We use Mason's gain formula for calculating the overall transfer function of the system. Okay, so every block can be represented by signal flow graph, but it is not possible to write signal flow graph into a block diagram. It is, but converse is not true. Okay, reverse is not true. There is some comparison between block diagram and signal flow graph methods. So in this, every element is represented by a block. Here every variable is represented by a node. Every variable signal is represented by a node. Transfer function of an element is shown by is shown inside the block. Here transfer function is shown along the corresponding branches. On the branch we show the transfer function. Overall transfer function of the system is obtained by block diagram reduction. Here it is obtained by Mason's gain formula. We obtain overall transfer function by Mason's gain formula. Then it is a time consuming method. It is a lengthy, time consuming, complicated method. Here it is not that much time consuming. It is a little bit simpler, easier method. By using Mason's gain formula, you can calculate overall transfer function directly, and it is simple to calculate this Mason's gain formula. Summing points and takeoff points are present here, so it makes the diagram complicated. Here it is removed, they are replaced by the nodes, so therefore it becomes very simple. Then self loop do not exist here. Self loop do not exist, but here self loops are present. So this was all about the signal flow graph theory, and in next video we'll see the Mason's gain formula and how to calculate overall transfer function for a signal flow graph. Till then, please stay safe, stay at home, and keep learning. Thank you.